Question 8. If you haven't gone through the chapter 11 PowerPoints, definitely do that before you watch this video. Otherwise this is going to make little sense than it already does. But since I know you guys study so hard for these things, I'm going to assume there's a lot of asterisks there, that you guys have gone through that content, and what I'm going to say doesn't sound like gibberish. So, question 8, you've got a table. Let's go through the table first, because that is part A. You need to draw your network from the table. First up, you got the Rocky Bank Reservoir. That's there. And it's gonna, from that, it's gonna go into Marginal Dam. And then from Marginal Dam, we're gonna have 3 breakaway points. So from Marginal Dam, you're gonna go up here to Freeland, gonna go here to Waterlogged, and then down here to Jonesville. This is about water moving through a system, so water moves all in one direction here. And then over on this side, we're going to have, there's going to be a demand, which is your location E, so they're all going to flow into the same point. So your demand point E. Again, they're all flowing towards E, so traveling in the one direction. We've got quantity in kiloliters per minute. So from here it's 1,000. From the other places it's got 200, 200, and 300. And then the demand here is going to be the same. So we're going to have 200, 200, 300 here as well. That's part A done. So part B, work out the flow capacity of the network. So the flow capacity of the network is going to be taken from this bit in red. When I'm talking about flow capacity, all I'm looking at is that little box in red. So we know, or we should know, what our flow capacity is. For those of you who don't know, flow capacity is the flow capacity of an edge is the maximum amount of flow that an edge can allow if it is not connected to any other edge. The flow capacity also is related to our inflow, which is the total of the flow of all edges leading into a vertex, and the outflow, which is the minimum value obtained when one compares the inflow to the sum of capacities of the edges leaving the vertex. Alright, let's break that down first. Inflow. Our inflow is going to be the point of, well, the amount of water flowing into an edge at any point. So the only point here in the box that I've drawn up in red, where something is flowing in, is from red to N, sorry, R to N, and that's got an inflow of 1,000. So this inflow is going to be 1,000 kiloliters per minute. Just going to check, you can see that, yep. Alright, then we've got the outflow. Alright, so the outflow is the amount of water moving out at any one point. the minimum value obtained. So in the box in red, the amount moving out is 200, 200, 300. So we've got 200, 200, 300. So at any point, the maximum amount of water, sorry, the minimum amount of water we can have moving out is 700. We can allow 1000 kiloliters to come into point M, but leaving point M we can only have a maximum of 700. Which means the maximum or the flow capacity of our network, the flow capacity of our network at any given point where we don't overflood the system, because we're working with water, is 700 kiloliters per minute. This 700 is our maximum flow capacity. So that's part B. Alright, so for part C, we gotta check if the demand is sufficient. So before we do that, I'm gonna quickly pause the video and remember to hopefully unpause it. Alright, now looking at demand. So when we look at demand, we're looking at this new box that I've drawn up in red. So the demand of our network is basically says that the amount of water coming out at N going into these three is that demand met going into N. In other words, do these and those numbers equal each other? If they don't, these numbers can be lower. You can have 700 going out and then only 900 maximum 900 able to come in. That's fine. We're not going to flood the system. But if we've got 700 going in and say 850 coming out, that demand's not going to hold because we've got a larger demand. Sorry, go back. If we've got 850, for example, going out from M and only a total of 700 that can go from each of these little stations back to the end point, that's not going to work. That's going to break our system. And that is what we're going to check by demand. So in the system, the amount leaving M or the outflow at M outflow at M is going to be 200, 200, 300, which we set up here is 700 kiloliters per minute. I think I'm going to have to... Oh crap, battery's going to die. Alright guys, bit of technical difficulties, needing an extension cord, but we're back. Alright, so the outflow at point M going away is 700. So let's look at the amount, the inflow towards E. So the inflow to E is also 200, 200, 300. So that's 700 kiloliters per minute. Since both of these two equal each other, that means the amount going out and the demand going into point E, the last point on our network, is the same. Therefore, we can say therefore the demand of the network is sufficient. And that's the end of question 8. I'm not going to do part D. You guys can have a go and work out how part D fits into all of this, because I can't give you everything. Alright guys, question 9. Very simple stuff. Planar graphs. So which one of the following is planar? Basically, planar graphs are any graphs where the lines don't overlap. So if I just draw the first one, I've got A, B, E, some point over here is D, and then I've got a point C over here, where an edge from A and an edge from E connect. To make that graph planar, what we're going to do is redraw it. So the lines, this edge here and that edge here, these two edges don't cross any other edge. So I'm going to draw what I have at the start. A, B, E, D. Some point C is over there. Alright, so in green, I'm going to make it a planar. So I'm going to take this line AC, and I'm going to go around. That wasn't green. You don't have to put it in another color, but I'm just going to do that to show you. So in green, there's the line AC, and then I'm going to do the same for line EC. Once you've done that, you've made a planar graph. Alright, so question 9. You've got this network, you're making it planar. Basically, these two lines that overlap, instead of going through and making them overlap, you're going to go around. So AC goes around this way, doesn't overlap anything here. EC goes around this way, doesn't overlap anything there. That makes the graph planar. Guys, question 11 on your worksheet doesn't work. Because, you know, when I was making it up, it didn't work. So, for that, you're going to do question 1. A, B, C, D. So question 11 is going to come from your textbook. I'm just going to change the question on the revision sheet. It's going to be exercise 9.4, page 315, question 1A. Alright, so here you've got 400 invested at the end of every 6 months for 12 years at 12% with interest compounded 6 monthly. And you have to work out the amount at maturity. So for your annuity formula, amount at maturity just means work out what A is. So write down your annuity formula, which is that one. Which is not that one, because the one you wrote is wrong. It's 1 plus I to the power n take 1 over I. Sorry, I was writing the wrong formula. Apologies in advance that Emily's gonna lose her crap. Alright, next. Put in the values you know. So in part A, you've got $400 invested every 6 months, so that's 400 there. Your rate is 12% compounded 6 monthly, so 1 plus 0.12 divided by 2, divided by 2 because it's every 6 months, it's going to be 12 years, so 12 times 2, take 1, divided by 0.12 divided by 2. If you do this bit on your calculator and just have a value for I, you can do that. I just haven't had the time to work that out, so I'm just going to write it like that and just let the calculator do it for me. And then once you put that into your calculator, you got 20,326.23. So at the end of your, at maturity, you've got $20,000. Alright, I'm gonna attempt to do question 10. Alright, so with question 10, you've got this diagram here. You've got to draw a network or a spanning tree from that. So we're going to start in the dining room. Then we've got a connection to the kitchen. The outdoor area doesn't have a name, so I'm going to leave that. Then we've got the sitting room here. Then from the dining room you can go to bedroom 1, you can go to bedroom 2, bedroom 3, bedroom 4, and the bedroom 1 also has a walk-in closet, so let's just put that in there. Walk-in closet there. From the dining room, we can go to the entry, and then to the front porch, Jesus. And then here you've got 2 storage rooms. Got a storage room and a utilities room. And I missed the bathroom. So right next to the entry, from the entry you can go to bathroom 1. And this is meant to be bathroom 2. Alright, so I haven't measured anything, but in the question, you'd have to measure it. I'm just going to assume my measurements are 2 meters, 2 meters, 3 meters, 2 meters, 4, 2, 3, 4. And then from the bedroom 1, we've also got a balcony. Doesn't look like there's stairs, so you can, and then from the balcony you can also go into the sitting room. That's what my house looks like. 2, 4. Alright. Obviously this is not to scale, this is not remotely correct in terms of measurements, because I've just randomly put numbers there. But for you guys, you're going to have to take the numbers, like measure it properly and work it out. Alright, from this, we're going to draw our standing tree. We're going to start at the dining room. So I'm going to rub this out. Alright, from that, our spanning tree will look something like the following. We're going to start with the dining room. Our lowest number is 2, so we're going to connect all the 2 pathways. So we have 1 to the sitting room, 1 to the kitchen, 1 to bedroom 3, and 1 to bathroom 2. And then I'm going to connect my third pathway, so these are all 2s. And then I'm going to move up and connect anything with the 3, because that's how Prim's algorithm works. 3, 4, so that's the 3. This is the 3. Bedroom 1. This is also a 2, so we can connect that because there's no loop. There's also, yep. And then I'm going to connect any 4s. So that's a 4 there. Alright, yep. I've got this 4 here. I can't put that 4 there if we close off our loop, but I can put that 4 there. And then I'm going to put my 2, 4, 4. And then bathroom 1. Yep, that's it. Let's say that's a 2 as well. Alright, once you got your spanning tree, that is the minimum spanning tree. You need to calculate the cost per meter. So, total not cost, total length. Total amount of meters, actually. We're going to have 2, 2, 2, 2, 2, 2. So 1, 2, 3, 4, 5, 6. So 2 times 6. We're going to have 1, 2, that's it. So 3 times 2. And then your 4 connections are 1, 2, 3, 4. So then our total cost, yep, still on the screen, is going to be 2 times 6 is 12, 3 times 6 is 3 times 2 is 6, 16, 16 and 12 is 28, 28 and 6 is 34 meters. Then it tells you that the cost per meter in the question is 9.5. So total cost is going to be 34 times 9.5. Which is $332. Alright, so the question in your exam isn't going to be straightforward as this, but it will be similar. You will have to draw a network, and then you will have to work out the total cost of wiring a office or something, I think, in the question. So it's the same concept, not exactly the same way of doing it.